my dear friends, let me introduce our speaker who is going to take this session. He is a young scholar from IIT Roorkee. He's completed his doctorate in the field of earthquake resistant building. So he has designed some structure, some building, and which can resist the earthquake of a high intensity. So we will talk about all the earthquake related issues. So I would request him that he can begin with the what is earthquake, what kind of damage is being done, how it is going to affect our buildings, and what are the various causes which result into the havoc, particularly why the people are killed in large numbers when there is an earthquake. But there are certain countries like Japan, they have developed certain measures. Their buildings are more resistant in comparison to the buildings which we construct in our country. What are the reasons behind that? Why there are certain pockets in the world where these earthquakes come very frequently? So all such issues we will try to learn from his session. And this is a very, very important session that you will be able to learn. The people who are from the civil engineering background, they will have more information, but the people who belong to the other profession, other discipline, they will be also benefited. Particularly when we are going to construct any building, then we have to think about, we do not think about the 5 to 10% increase, and if it becomes safer. So that safeguard should be taken prior, it should be inbuilt in our planning rather. So many a time if the planning is done, then in the same cost we can construct our building and it will become earthquake resistant. But these days, all of the places we are flooded with the various private builders and they are not taking care of the norms. So even the urban bylaws or the city bylaws, which says that they should also make earthquake resistant houses or buildings, but they are not taken care of. But gradually, certain administration, certain government, certain state governments, they have taken a decision that they will pass the buildings, only those buildings which have some inbuilt earthquake resistant features. So that kind of things are there, but we have to take care of the construction, particularly in the Himalayan regions or what we call zone 5. Rather, we have reduced the zone number, only 4 zones are there these days. So he will also discuss what are these 4 zones and why earthquakes are more frequently come in the Himalayan zone, what are the regions. And later on he will discuss about some mitigation and whatever the research he has conducted, particularly related to the earthquake resistant structures. So that research contribution will also be given to you, that what kind of contribution is made. So I would request all the fellow participants from all the 5 centers, they should be ready, and I would request the coordinators to call other people because this is a very important lecture, otherwise they will miss it. So let us begin this session that is on earthquake resistant houses or earthquake and its mitigation. So both is the same. So we have to take some mitigation, and that mitigation comes in the form of better housing, better retrofittings, and better casing our houses. So let me invite Mr. Siva Chidambaram. Now he is a Dr. Siva Chidambaram, got his degree from IIT Roorkee and presently teaching at Thapa Engineering College, that is a university, technological university. And that is a good thing that he has been also selected as a scientist in CBRI, Central Building Research Institute. So after 2-3 months, in the month of December, he has planned to join there after completing his syllabus at Thapa Engineering University. So let me invite Mr. Siva Chidambaram So kindly be with us. Let me invite Mr. Siva.
Very good afternoon to everyone, and I owe my gratitude to Professor Ewan Roy for inviting me to this lecture. Myself, Dr. R. Siva Chidambaram, working in this area for the past 6 years, and we are going to discuss today's earthquake disaster and its mitigation. So first, this is the Earth interior look. So as of now, if you know the Earth exteriorly, from the exterior point, we can say our Earth is going to be a simple and unique, and is integrated with each other, right? That's perfectly right. So when you look into the interior part of the Earth, you can see the very most inner core, outer core, mantle, upper mantle, and crust. Crust is the region where we are actually. So inner core is a very solid part, and outer core is in the liquid form, or in the inner core is in the solid form, outer core is in the liquid form. Remaining are composed of sand and rocks. So at crust, Earth has four major layers. So one is inner core, outer core, mantle, and crust. Crust is the region where we are actually. So the crust and the top of the mantle make up the thin skin on the surface of the planet. The skin is known as tectonic plates. Tectonic plates are nothing but a plate kind of form, which is made by rock materials. Say we can say directly it's a rocky things. Just imagine below the mantle, exactly near the mantle, we have many rocky surfaces. Like when you have a water, and just if you are floating any leaves on the water, how it will float. Similar kind of things, that these kind of tectonic plates will be exist in our Earth surface. So it is exactly below the mantle surface. So these tectonic plates are not a continuous plate. So before 1900, we used to thought that these tectonic plates are continuous plates. But later, after 1920 and after 1960, finally we concluded in the year 1960, these tectonic plates are not a continuous plate; these are broken plates. So broken plates means these are it's not a continuous plate actually. So it is broken plate. So just imagine when you have a cup of water and we have many leaves, broken leaves. Okay, so these leaves will float. So it is not going to be in ideal position. Same kind of things are happening internally in the Earth surface. So these tectonic plates will keep on moving to the different directions. We can't say this is moving in this direction, this is moving in this direction. These tectonic plates will keep on moving in any directions. So in our Earth, we have 7 tectonic major plates and many number of sized small plates. So you can see in this picture, Pacific plate, North American, Eurasian, African, South American, Australian, and Antarctic plate. These plates are generally referred as 7 major tectonic plates. So when you look into the Indian plate, exactly Indian plate, if you look into the Indian plate, you can see Indian plate is perfectly connected with Eurasian plate. And this Eurasian plate is one of the major plate, and Indian plate is one of the sized continental plates. So I told you we have 7 major tectonic plates and many number of sized small tectonic plates. So in this case, our Indian plate is one of the smallest plate and is perfectly connecting with Eurasian plate, which means our plate is merging with Eurasian plate, exactly in the region of Himalayan belt. That's why it is generally referred as one of the very active seismic region. That particular Himalayan region is generally referred as very active earthquake region. That's why we used to have many earthquakes in those regions. Because when two plates are merging or colliding with each other, we can expect some earthquakes. You can see the third image, Eurasian plate, Philippines plate, and Pacific plates, where we have Japan exactly. In our case, our Indian plate is merging with Eurasian plate. That's why we are having earthquake. So in this case, there are 3 plates are merging with each other. Exactly, our Japan locates in that location. That's why Japan is generally facing more number of earthquakes than any other country in the world. So before that, we have to see when 2 plates are colliding with each other, there is a possibility of one over another, and another one is like one gets apart from another thing. Like when two plates are merging, see in this the third picture, continental crust is going upward and oceanic crust is going downward. In those kind of movement will create a mountain. For example, our Himalayan mountain is one of the perfect example. And similarly, suppose if two plates are moving in opposite direction with each other, so there is a possibility of rift. There you can see, or there you can form. There is a possibility of natural ozone formation over those locations. Earthquake. It's not a bad thing, first of all. It's a very good one. It's nothing but releasing a sudden energy. So humans are living on the crust, which means the uppermost part of the earth. Okay, so we are thinking that earthquake will kill us. No, earthquake is not going to kill you and me. The building which we are constructing on the earth's surface will kill us. So that we have to construct our building to be an earthquake resistant one, so that we can resist certain amount of earthquakes by using some modern advanced techniques, and you can easily survive during an earthquake. So earthquake, basically I told you, when two tectonic plates hits with each other, there you can expect certain amount of vibration. This vibration will release in the form of energy, because I told you tectonic plates are rocky materials. Rocky materials means it's an elastic material, basically elastic material. So these elastic materials will store its elastic energy internally. When two plates hits with each other, this elastic stored energy will remove or will come out from the surface, from the internal part of the earth. That point is generally referred as focus. So basically, I told you tectonic plates are rocky surface, but it's not going to be a rigid surface always. In some part of the rocky surface, we can expect certain amount of discontinuity in the continuous mass. So this particular discontinuity is generally referred as a fault. Well, that is the weakest part of any tectonic plates. So when earthquake occurs, we can expect earthquake because of exactly in the fault region. So focus is the point where exactly earthquake originates internally in the earth surface, and epicenter is the point where the earthquake dissipates an energy on the upper surface of the earth. So exactly in this picture, you can see what is fault, what is focus, and epicenter. There are two rock surface you can see. One is left side and right side. Both are two different plates, and they are colliding with each other exactly at the point focus. And epicenter exactly is the straight point on the upper crust where we can expect our earthquake point. That is generally referred as epicenter. Whatever the forces it may be, even if I speak, everything will form or will travel in the form of waves. Similarly, earthquake energy are also dissipated in the form of waves. That is generally referred as seismic waves. So in this case, we can differentiate the waves into two categories. One is body waves, another one is surface waves. Body waves means these waves will travel internally in the earth, where surface waves we can expect on the surface of the earth. That is the difference between these two. So P waves and S waves lies within body waves, and love waves and Rayleigh waves lies within surface waves. So body waves are the first one will initiate from the internal part of the earth, and surface waves is the continuation of the body waves will travel on the surface of the earth. So what is the difference between these two? P wave is a primary wave. That is the first wave will start after an earthquake occurs, or the first wave which will reach any seismic station to inform us some earthquake is initiated internally on the earth surface. Next one is S waves. S waves are generally referred as secondary waves or shear waves. These waves are followed by primary waves. So what is the difference between these two? I told you in the very first slide, our internal part of the earth has different layers. One is inner core, it's very solid, and the next one is outer core, is going to be in the liquid form. Third is our normal mantle. So these waves will start from the inner core and will travel to the surface, which means the crust. So in this case, P wave can travel in any medium, which means solid or liquid. But S waves won't travel in the liquid medium. That's why we can't see S waves during this, in the surface area, as well as it can't reach or it can't cross the outer core. Inner core is solid and outer core is in liquid form. That's why it will withstand always within the inner core. It can't cross the outer core. Whereas love waves and Rayleigh waves are not going to be a defined waves. Love wave, the reason why we have love waves. This was invented by, it's not invented, this was exactly like noticed by A.E.H. Love, a professor who noticed this and mathematically modeled this wave. That's why it is generally referred as Love wave. And Rayleigh, Lord Rayleigh, who mathematically modeled this wave, and that's why it is generally referred as Rayleigh waves. These two waves are very strong waves as compared with the body waves, because body waves will easily dissipate, but the Love waves and Rayleigh waves will travel on the surface of the earth. That's why these two waves are the major source for any disaster on the surface of the earth, whereas body waves won't. You can see the first picture stands for the primary wave or P wave. This will travel like this. No, it will travel on the surface, only the surface, not in the internal surface, only on the surface. That is the harmful one, yes. Love wave and Rayleigh wave are the harmful waves. The next one, B, you can see the secondary waves. So when you have a rope, and if you play with the rope like this, the rope will travel in wave form. This is the way the S waves are traveling in the Earth's surface. Internally, is the interior waves, this is the body waves. Whereas come to the C, it is like in zigzag form, and whereas come to the D, that will travel in a wave form plus it will squeeze. That's why Rayleigh wave is one of the very strongest and very disaster wave that will create huge disaster on the surface as compared with any other waves. So primary waves are the very fastest wave, but Rayleigh wave is one of the very, very strongest wave which will create huge disaster on the Earth's surface. So how to measure these things? We have two different kind of measurement for earthquake. One is magnitude, another one is intensity. So what is magnitude? And this will be measured in the term of Richter scale, whereas intensity will be measured in the term of modified Mercalli intensity scale. There are two different scales we have. So what is magnitude actually? Magnitude defines the amount of energy released during an earthquake. So amount of energy, I told you, is a stored elastic energy released due to the collision of two tectonic plates or many. So during this collision, we can expect the stored energy to like when you have a pressure cooker in your home. So it will create pressure internally, and whenever it requires or whenever it feels that pressure is very, very huge, so automatically it will release. Same kind of thing is happening internally in the Earth surface. So that release of certain energy will be measured in the term of magnitude. That will be measured from 1 to 9. So in this case, you can see we have a slight when the magnitude lies within 5, and it is moderate for 5 to 6.9. It's a great 7 to 7.9, and very great is more than 8 Richter scale. So what is the difference between even like 4.9, 5, 6.9? Say for example, 4.9, we have some earthquake occurred in the magnitude of 4.9. Next year, in the same location, we are observing another earthquake with a Richter scale of 5.9. So it seems to be 1. 4.9 to 5.9 is only 1 Richter scale increase. But in actual, it is 31 times higher than 4.9, which means the amount of energy, for example, the amount of energy measured during 4.9 is 100. So the amount of energy will be released for 5.9 is 31 times the 100. So it is 31 times higher than the 4.9. It seems to be single, like 4.9 to 5.9. It is not 1. The 1 is which is equal to 31 times the energy released in the 4.9 Richter scale. So this will talk about only the magnitude, which is amount of energy released. For example, if earthquake occurs exactly at Chandigarh, so here the magnitude is going to be, say, it is magnitude is 7. So even if you measure the earthquake at Tamil Nadu or at America, the magnitude is going to be same. 7 is going to remain 7. So let us see modified Mercalli scale. This is talking about intensity. So what is intensity? Intensity is nothing but the amount of disaster we faced. Like when earthquake occurs exactly in Chandigarh, so the buildings which we have constructed on the earth surface in Chandigarh will be collapsed or will get damaged. So this damage level is nothing but the intensity. The amount of disaster occurs, the amount of what can I say, like what are the damaged portions, how that structure is damaged. According to these things, we have created scale that is generally referred as modified Mercalli intensity scale, MMI scale, ranging from 1 to 12. Ranging from 1 to 12. So 1 stands for not felt by people, whereas 12 stands for huge or total damage. So, for example, I told you, if earthquake occurs at Chandigarh with a magnitude of 7, even if you measure at America, the magnitude is going to be same, 7. Is not going to change, but the intensity will differ. So in America, the intensity is going to be 1, whereas in Chandigarh, the intensity is going to be 12. So that is the difference between intensity and magnitude.
What is the difference between zone and grade?
So grade is nothing but a scale. Grade number 1, grade number 2, grade number 3, like scale number 1, 2, 3, 4. So it is 1 to 12, that's it. Zone is completely different. That is different. Next is seismograph. One of the image which you are seeing is a very old image. This is nothing but seismograph, where you can see a suspended ball with a pen, and here we have a rotating drum. Over the rotating drum, they used to have some graph. So what will happen? This suspended ball will always in suspended form. So whenever earthquake occurs, this ball will move. So when the ball moves, so automatically those movement will be recorded in the rotating drum. So that is generally referred as seismographs. These seismographs are one of the very, very oldest equipment to note or to monitor or to observe the amount of earthquake, amount of energy released in the form of acceleration or velocity or in the term of displacement. Right now we have very advanced equipments, which you are seeing is one of the advanced equipment, the same thing, but in an advanced form. Where instead of the weight and pen, we have an automatic pen, which will always in the moving form, and bottom we have a rotating drum. Now, this machine is also not available. We have accelerogram directly that will record the acceleration of the particular earthquake or velocity of the particular earthquake or displacement of the particular earthquake directly. Here we have to get the graph separately and we have to analyze. Whereas in the recent form, we have advanced equipment which can easily measure the acceleration or velocity or displacement directly during an earthquake. Basically, these seismic stations will not be on the Earth's surface. Will be 20 or 30 or 10 feet, 20 feet or 30 feet below the Earth's surface, because these equipments are very sensitive. Even if you speak, or even if you jump, or even if you're traveling with the vehicle on the surface, it will record all the vibrations. That's why we used to keep all the seismic station below the ground surface. So you can see a model accelegraph where the first stands for P wave. I told you it's the first wave, which will inform any seismic station about an earthquake, followed by S wave, that is the secondary wave. These two waves are body waves. Let us come to the surface wave. This surface wave will create huge problem to the building which we have constructed, because these waves are traveling on the surface. Like this, for example, if your waves are traveling like this on the surface, and if you are constructing any house on the surface, so these waves will create severe demolition or disaster to the surface which we have constructed. That's why these waves are generally referred as surface waves, or very strong waves as compared with our body waves. So this is how the graph looks. This is how we have to separate the graphs to study or to monitor. Initially in the surface waves, the waves starting from S wave to surface wave, generally referred as forced. This is forcing the entire thing, and followed by, which means after peak, we can see a degradation in the graph that is called free vibration, which means take a steel scale and vibrate. So if you vibrate like this, so it will vibrate for about a second until you give vibration, and even if it stops. Okay, if you continue the scale vibration, this way scale will vibrate. But the thing is, even if you stop, the vibration is not going to be the previous level, but you can feel certain amount of vibration. Even if you stop the vibration, or even if you stop vibrating the scale, you can feel certain amount of vibration on the scale. That is generally referred as free vibration. So you can see what is forced vibration, what is free vibration from this wave itself. So this is Indian zone map of our seismic zone map of our India. So our previously, before 2001, before Bhuj earthquake, our India has 5 zones: zone 1, 2, 3, 4, 5. After earthquake, after some intraplate earthquakes, we have reduced from zone 5 to zone 4, 2, 3, 4, 5. So you can see this detail in IS 1893 2002. So in this case, what is zone 2, 3, 4, 5? 5 is the severe zone, whereas 2 is the moderate zone. Which means what? We can expect very normal and very moderate earthquakes in zone number 3. In very rare case, like zone 2, the earthquake frequency is very rare as compared to zone number 5. Whereas in zone 5, you can expect more number of earthquakes. That's the difference between zone number 2, 3, 4, 5. So that's a gradual increase. So I told you, our Indian plate is merging with Eurasian plate exactly in the Himalayan belt. That's why it is perfectly mentioned in the zone number 4 and 5. So zone number 4 is green color, zone number 5 is pink color. You can see our Bhuj area in Gujarat and other part of the Himalayan belt is marked by pink color and green color. So these are the very important point, important region, which stands for high number of earthquakes during an year. So we can't expect that earthquake will occur in next 6 months or in next 1 year. At any time it may occur, but the intensity is going to be very high in those regions. That's why it is perfectly marked by zone number 4 and 5. So what are the effects of earthquake? You can expect landslides, surface faulting, tsunamis, liquefaction, and flash floods. If earthquake occurs on the surface, we can say that is earthquake. If earthquake occurs below the sea, that is generally referred as tsunamis. So I told you earthquake is nothing but sudden release of energy. Okay, if the sudden release of energy happened below the ocean, what happened? Those water present on the sea surface, on the sea, has to absorb the energy and it has to dissipate the energy. So that thing is happening exactly in the sea level. So during exactly in the midpoint of the sea, the depth is going to be very large as compared with the shore level. That's why there is no sign of any wave movement during an earthquake occurring below the sea surface. But the tsunami will create huge disaster exactly in the shore level, not in the internal level, because the depth in the sea in the middle level is going to be as large as compared with the shore level. That's why the shore level depth is not sufficient to hold the energy released during an earthquake. That's why it is dissipating so that's why we can expect the tidal waves up to 10 meter height or 20 meter height. That is nothing but the stored energy, released energy. That is the wave is traveling, the tidal waves are traveling to a height of 10 meter or 20 meter. Is that waves are not traveling actually. That is nothing but the released energy is tending the tidal wave to travel up to that height. So what is surface faulting, flash flood? We will see in the next slide. You can see. So this is surface faulting. Surface faulting, I told you, fault means it's a two. It's breaking into two half. So you can see in the first two image. First one stands for landslide. Second one stands for faulting. And third one is nothing but flash flood. And the fourth one stands for tsunami. Liquefaction is, I didn't mention this liquefaction about, there is no slide for liquefaction. So liquefaction is nothing but, so below the ground surface, we have a groundwater table, isn't it? So when you vibrate, when the entire earth surface is getting vibrated automatically during an earthquake, what will happen? This water table will go or will come up. So when the water table is coming up, what will happen? Certain amount of settlement will happen immediately. That is generally referred as liquefaction. So these are the different type of failure modes which we observed during an earthquake. See, so basically you can see these kind of buildings in everywhere in our cities. Like this is generally referred as soft story building. Soft story building means in the ground story we have left the area blank for car parking, and above the ground story we have perfectly filled with bricks. Okay, that's why the above stories are generally stronger than the ground story. That's why it is generally referred as weak story or soft story. One of the very important part of the building, but it is being weak. That's why during an earthquake, immediately this region will fail and it will fall down like the second one. You can see in this picture, the second picture, the building had one ground story, but because of the ground story failure, the entire building comes down. Similarly, come to the fourth picture. Here also the same soft story failure occurred. So what is soft story failure? We will see in a video. So this is the building, ground story plus 5-story building. You can see this is being tested in sake table. Sake table is nothing but an equipment which will give you a certain amount of vibration. You can define an earthquake vibration. So that will apply the vibration to the particular building so that we can study how the building behaves during an earthquake, real earthquake. Okay. So this is a G plus 5-story building. The ground story, again, in all the story, there is no any brick wall. It is a bare frame. Okay. So during an earthquake, how the building will behave, you can see. Now they are applying vibration. So in this video, you can see the top stories are remain still active, but except the ground story. The ground story is completely collapsed because a soft, that is, I told you that this is a soft story and it is more flexible as compared with the other stories. The stiffness level of that particular story is very, very low as compared with the above stories. That's why exactly failure occurred in that particular story. These kind of failures are generally referred as soft story failure. I told you, if earthquake occurs below the sea level, then we can expect tsunami. This is how. The first one is the fault plane, where two plates collides with each other, and that the red mark is nothing but the focus point where earthquake initiates, and the energy is releasing. So exactly the next picture, you can see the depth of the sea is very, very high as compared with the depth in the shore level. So these waves are gradually travels and finally dissipates in the shore level. That's why the tidal waves are going to a larger height as compared with the normal waves. So these are the various codal procedures we do have with us. If we follow these codal procedures, we can make our structures an earthquake resistant one. So we are not trying to make our our building to be an earthquake proof building because it is very expensive. And if you're constructing or if you're designing a building to be in elastic limit, we can, but it is not required. That's why we are not using a word earthquake proof building. It is earthquake resistant buildings. So what does it mean? What is the difference between proof and resistant? Means proof, nothing will happen, whereas to resistant, something will happen to a building, but it is not going to collapse completely. That is the meaning for resistant, and there's a difference between resistant and proof. So this is a formal load-bearing structures, which means we have constructed the entire building with the help of brick and cement mortar with RCC slab if requires. So this is load-bearing wall. This is the entire structure is generally referred as load-bearing structures. All the loads are bearing by the wall and will transfer to the foundations. Maximum of the Indian buildings, the low-story buildings, low-rise buildings, are being constructed in this form only, using load-bearing structure concept, because it is quite economical as compared with RCC frames and very cheap, and it requires very non-skilled labor can also construct this kind of buildings. That's why maximum of the low-rise building is being constructed with the help of this concept. Whereas next one is moment resistance frame building or RCC building, reinforced cement concrete buildings. You can see we have foundation and columns and beams and slabs. So columns are traveling from foundation till the end of the roof, and we have intermediate members, that is transverse members, generally referred as beam and slabs. In this building, very important part of the building is not column, is not beam, the connections. Connections at all level. So you can see the foundation to column connection is very, very important. And similarly, beam to column connection is one of the very, very important part of this particular building. We will see why it is very, very important. So what are the things we can do? Earthquake resistant measures at planning stage. It should be start from the planning stage. Like, see, if you have a solid surface, we can execute the construction immediately from the foundation. Suppose if your foundation level is not solid, So if you are filling with soil, then filled up soil, our foundation should not be on the filled up soil. The reason is an existing firm soil has a very good consolidation as compared with the filled up soil. So you can't meet the consolidation level of the firm soil using filled up soil. So in such circumstance, you can go for raft or pile foundations, because we need pile foundation only in the filled up soil surface. Whereas in the firm soil, the consolidation level is already good, so there is no need to go for extra consolidation or any pile construction. So you can go for pile construction. The next one is, if your building is not only in rectangle shape, we can expect in T, L, U, or C shape, any shape. But the thing is, one building should not have contact with another building. So the first is T plan. The next one is how it should be. The T should have a separation joint. The reason is, if you have two sticks, just to take two stainless steel scale and keep with each other, okay, and try to vibrate it. What will happen? One steel scale will touch another steel scale. So what does it mean? The effect of one will create effect on another. That's why, that is the meaning for this. So when you have two different buildings, we should have a proper gap between these two buildings. So what will happen during an earthquake? Both the building will vibrate in its independent mode. So one vibration will not create any problem to the next building. That's the meaning. That's why we have to have separate joints between any part of the building. I told you, if your building has no connection, so the first image stands for how it should not be. The next one is how it should be. So when you have connection, the failure will exactly occur at the corner point. When you don't have any connections, both the buildings will vibrate in its own mode. So this is how it should vibrate. Next one is, we have water. Just give me that. So you can see this example. This is the water can I have, and now even if I vibrate the table, the water can is going to be ideal condition. The internal liquid in the water can is vibrating. Even still, the entire water can is also vibrating, but it is not falling down. The reason is the base is very solid, whereas the top has linear portion. That's why it is not falling down. Suppose if I keep like this, the base is very small as compared with the top. Now, even if I apply small vibration, the entire water can is collapsed. Okay. PPT. See this case. That's why our earthquake resistant design philosophy says that the foundation width should be higher than the top width, so that it can easily resist any kind of earthquake. So plan wise, we have to make our building so safe, and elevation wise, we have to make our building so safe. If we have different height buildings, again we have to make a proper separation joints. Otherwise, the vibration of one part will create adverse effect on the other. And always we should not have any suspended things or any external projection like cantilever. You can see in the next one, our foundation, the base story width is very low as compared to the top one. So those things are generally referred as floating one. Similarly, the third picture says that the first two columns is supported perfectly, whereas the corner columns are not supported by any column from the foundation. So when you're rising any column from any intermediate level, it should be properly connected with the foundation. If not, those columns are generally referred as floating columns. So these are the unsupported parts. It will fail immediately during an earthquake. So this is the recommended gap between two buildings in masonry. Similarly, we have a recommended gap for our RCC buildings, which is perfectly defined in IS 1893/2002. So what is liquefaction? I told you, so the groundwater table is coming up. That's why we can expect certain amount of sudden settlement. This is a perfect example for this. So in this case, we can't predict that liquefaction is going to happen below my building. In such circumstance, what we can do, we can construct our building using any pile foundation based or raft foundation based. This is a perfect example for raft. So raft is nothing but our building is going to be on the entire platform. Our entire building is going to be on a single platform. So one side liquefaction or one side settlement is not going to affect the another part. So or even if it settles, the entire building is going to settle perfectly in a similar way. So the settlement is going to be uniform everywhere. So it's not going to create any harmful defect to my building. Or you can go for pile foundations. Okay, it's not only for RCC roof building, it is perfectly defined for our normal slope roof building also. If you have slope roof building, the first image you can see up to the door level or up to the sill level, up to the roof level, we have interconnections. Like one side wall is perfectly supported with another side wall. Exactly at the gable end wall, where we have a triangle portion, the first image, that wall is not supported by any other walls. So what will happen during an earthquake? That is unsupported part, so immediately it will fail. Just look into the second one. In such circumstance, we should not go for the triangular wall, that is gable end wall. We have to go for hipped roof, which is perfectly defined in the second images. So not only in the roof level, we have to make our entire truss in this form so that it can easily resist any kind of lateral movement. Similarly, in the RCC buildings or in the load-bearing structures, the parapet wall is again one of the very important unsupported wall. So it is again unsupported. So during an earthquake, immediately it will fall down. So this particular unsupported wall should be perfectly connected with our any structures very close to it. So this is the way we have to perfectly connect the parapet wall with our existing structure so that it will not fall, it will not fail during an earthquake. Similarly, water tanks, one of the very, very important part of the building, which supplies water. At the same time, one of the very, very crucial part of the building during an earthquake. So it is again unsupported. It should not be. So when you are constructing a water tank along with your building, we have to follow certain procedures. Otherwise, it will create a sudden collapse at the top level. So that will create huge stress to the next stories. So in masonry building, so masonry structures is perfect example. It can resist any kind of compression load, but it is weak in tension. Just see the next one. When you apply tension force, the mortars are going to fail immediately. So our masonry structures are good in compression, but weak in tension. So I told you that our masonry structures are weak in tension. So it is very difficult to construct a long wall using masonry structure. Even if you want to construct a long wall, we have to go for cross wall, or otherwise we have to create a buttress at specific level. So when you are constructing a buttress, the buttress will give you external support to the long wall, or otherwise we have to go for cross walls as defined in these images. So it's not only for brick masonry, this is perfectly applicable for the stone masonry also. The stone masonry is not like a sized stone, it is a random rubble masonry. In this case, the stones are not going to be in uniform size like our brick. So we can't follow any English bond or Flemish bond or British bond, anything. We can't follow any bond methods. So we have to construct in this fashion, one of the traditional way. But what we can do, we can keep some through stones that will connect this layer with this layer perfectly at different stages, like defined in the first one. We are constructing like the second one, but we should not construct like the second one. We have to construct like the first one in the depicted pictures. This through stone should be followed, the through stone methodology should be followed in the wall connections, because in the wall connections, we have to keep the wall connection. If you have a wall like this, if you are connecting like this, what will happen? There is no perfect connections. So during an earthquake, this wall will fall like this wall will fall like this. So in this case, when you are connecting the wall like this, you can create, when earthquake occurs, it can jointly resist any kind of forces. That is why we have to go for through stone as defined in this picture. So not only through stone methods, that is one of the very simplest method. When you are constructing a masonry structure like this, we have to go for band. You might have seen a small beam kind of structures in masonry structures that is generally referred as lintel. Or in the previous old construction, we used to have a long stone over the door or over the window. The reason is the wall structure above the window or above the door should not rest on the door frame or window frame, because these door frames and window frames are not designed to resist such a load. That's why we used to have a long stone. Nowadays, we are not following that. We are having lintels. Okay, lintels. So what we are doing in lintels, we are constructing lintel with the help of small steel rods for a small depth with the help of concrete, plain concrete. Jointly, it is a reinforced concrete element. These kind of similar to the lintels, we have to follow those kind of structures at different level, at plinth level, lintel level, and roof level. Those things are generally referred as band. That is plinth band, lintel band, and roof band. What is band? I will tell you in the next images. And plus vertical reinforcement. Vertical reinforcement, this is not RCC building, this is masonry structure. Vertical reinforcement means we are not recommending 4 to 5 vertical reinforcement at a single corner. So only one reinforcement at every corner and every openings, wherever we have openings. Like this image, the corner we have a vertical reinforcement. Exactly at the door opening and window opening, we have vertical reinforcement. So this is the vertical reinforcement and band. So our IS code is not only recommending the steel, it is recommending the bamboo stick also, or cane wood. You can go for cane wood, or you can go for bamboo sticks to make the band. This is how we have to make the band and vertical reinforcement. This vertical reinforcement will perfectly interlink both the band in X and Y direction, and it will create the integrity between these two. So this is how the reinforced concrete band will be. So for T connection, we have to follow the first procedure, and for corner connection, we have to follow the second procedure. So it is perfectly defined in IS 4326 code book. You can follow this IS 4326. So that is earthquake resistant measures for masonry structures. So these are the various failure images, failure of buildings we observed during an earthquake. So another interesting fact that I told you that M 4.9, it's a magnitude of 4.9, and which is as compared with 5.9, it is 31 times higher than 4.9. M 6.3, which means 6.3 magnitude Richter scale, the amount of energy released during an earthquake having a magnitude of 6.3, which is equal to an atom bomb which was happened in Hiroshima, Nagasaki in the year 1940s. The amount of energy released in 6.3 magnitude, which is equal to the amount of energy released during an atom bomb failure or atom bomb disaster in Hiroshima, Nagasaki. Both are equal. 6.3 magnitude is equal to an atom bomb failure. So this is how the failure occurs during an earthquake. So this is a building, it's masonry building. So this is how the building wall will subject it to deform during an earthquake. If it is not perfectly connected at the corner levels, the one in this Y direction will behave like the first one, B in X direction will behave the B component. So what we are trying to develop in the masonry structure is to create a box action. If you have a box, square box or any rectangular box, keep the box on the any platform and vibrate the box. The entire box will move. Suppose if you are connecting if you are creating the box with the help of small thermocol sheets or any pad without any perfect connections in the corner level, and you have created a dummy box and it is subjected to a vibration, what will happen? The corners is perfectly, if the corners are perfectly connected, the box will resist any kind of vibration. If it is not perfectly connected, the box is not going to resist any kind of vibration. So what will happen? When the entire box is subjected to vibration, the box connections will fail in the very initial stage, so the entire building will collapse. So this is how it will behave during an earthquake. That's why we are recommending the corner stones in the corner levels. So if you have perfect connections in the corner levels, the entire building will behave like a box. And similarly, staircase. When you are constructing a staircase in any building, it should be separated from the building, because staircase is a reinforced concrete element, whereas our masonry structure is not a reinforced concrete element. So it should not have a perfect connection. It should have a perfect gap between these two structures. So when you have a building, masonry building, during an earthquake, it will behave like this. In order to address this issue, we are recommending different level of roof band, lintel band, and plinth band, and sill level band if requires, plus vertical reinforcement. When you have vertical reinforcement and band, the building will deform gradually. This building will have damages during an earthquake. We are not telling the building is not going to damage. It will damage, but it is not going to collapse. It is not going to kill you or me. The one who is going to be in this house will be perfectly safe during an earthquake. So when you have open windows like this, exactly at the corner level, huge cracking will occur. This cracking will allow the entire building to collapse. When you have vertical reinforcement and lintel band and sill band, these bands will perfectly connect and will perfectly resist any lateral deformations. Suppose those recommendations are for new buildings. When you have an existing building and if you want to upgrade the building, so what we have to do, these are the various procedures. I told you we have to make a through stone in random rebuild masonry structure. But in the case of existing building, it is very difficult. So what we can do, we can make small holes and we can fill the entire small hole with the U-shaped or hook-shaped reinforcement steel rod. That's a very small steel rod having S shape. It is defined in the first picture. The remaining gap can be filled with any mortars or any concrete. Similarly, for masonry structure, I told you we have to go for a vertical reinforcement at corners as well as the openings. But in existing building, it is very difficult to have a vertical reinforcement. So what we can do, we can go for weld mesh in the both sides, internally and externally. Both the weld mesh, internal and external, will be perfectly connected by a interlink steel bias. Now, when you plaster the entire internal surface and external surface, it is going to be external reinforcement. So it will resist any kind of deformation, lateral deformation. So this is how we have to upgrade an existing building to be an earthquake resistant one. So far we have discussed about earthquake resistant measure for the masonry structure. Now earthquake resistant measure for RCC frame structure. See, for minor earthquake, we can expect, and this is the RCC reinforced concrete building with infill frame. This is infill means brickwork. Internally we have brickworks and the outer frame is RCC frame. So during a minor earthquake, we can see the internal brick walls are cracked. Let us come to the moderate shaking. When the earthquake is in the moderate level, the crack occur in the brick wall is creating stress exactly at the beam, exactly at the column connections. When you come to the third picture, during severe earthquake, these structures, the brickwork is creating huge distress to the beam and as well as the beam column elements. Plus, the deformation occurring due to an earthquake is also exactly at the beam column connections as well as in the foundation connection. That's why I told you in the very first stage that foundation to column connections as beam to column connections are very important point, so that you can easily resist any kind of deformation with any kind of earthquake. Otherwise, the building is not going to deform. Which means what? Take an example of coconut tree and banyan tree. During severe wind, a coconut tree can deform like this easily. Finally, it will come to its original question. When you come to banyan tree is not going to deform. It is going to resist the wind force up to a certain limit. After that, it will completely fall down. It is not going to resist. When you come to coconut tree, it will, from the ideal position, it can travel to this, finally, it will come to its original position. So that is the perfect example for an earthquake resistant building. The building should behave like this. So, but our concrete members or our concrete is not a ductile material, it is a brittle material. It is not going to deform like the coconut tree. So that's why we are introducing steel reinforcement in the concrete members. That's why it is generally referred as reinforced concrete members. So these are the various failures occurred in the reinforced concrete buildings during an earthquakes. You can see in this image, the top stories are still active as compared with the ground story, because the ground story is the weakest part and soft story. So this failure is generally referred as soft story failure. The next one is a bridge failure during an earthquake. So first one, second one, see the third one. 1, 2, 3, 4, 5, 6. It is a 6-story building, but there is no column actually. All are one over another. So what happened actually in this case? It is not perfectly designed. During an earthquake, these columns are not able to resist any deformation, so the column failed. So the entire one floor is resting on another floor. So it is a 6 to 7-story building, a perfectly packed like a burger. See the another failures. These all are soft story failures. You can see the top story is still active, but the bottom story is failed. Another point is, see, these are the improper construction, example for improper construction. So what does it mean? That we will see later. See, in this first image, the way we have vertical reinforcement, we have concrete. We are not able to see any lateral reinforcement. When you come to the second image, it is perfectly confined, but still the confinement level is not up to the mark. The third one, fourth one, and fifth one stands for the perfect example for shear failure in columns. This is also because of improper confinement in the column. So this is what they are expecting. The first one, hinges. Hinges is nothing but, you can see, you might have seen hinges in the door. When you open the door, you can open the door. When you close the door, you can easily close the door because the door is perfectly connected with the door frame with the help of hinge. If you are not having the hinge, you can't open the door, you can't close the door. Same kind of hinge formation should be occurred in the beam column joint connection as defined in the first one, A. Location of potential plastic hinges. So we are not going to construct, or we are not going to keep the hinges in the door. We are not going to keep any hinges like that in the building frames, but we are expecting the entire frame should behave like a hinge. The entire particular location should behave like a hinge, so that the entire building can deform like this. Otherwise, what will happen? So this is the building, and when it deforms, it should deform like this, or it should deform like this, the entire building. So what will happen if this is the beam and this is the column? We have a support like this. If my column and beam connection, this is the connection point, and if the connection point is so rigid, so what will happen? If it is not allow the entire building to deform, when we apply the lateral deformation because of an earthquake, what will happen? This joint will fail immediately. So what will happen if the joint fails? The entire building will fail. So if the joint is allowing the entire building to deform gradually like this, what will happen? We can expect certain amount of deformation. We can resist certain amount of deformation. So my building can go up to a certain amount of deformation to resist an earthquake. So this is like the behavior of your bamboo tree. Okay, so this is possible when the plastic hinges forms exactly at the desired locations as defined in these images. If not, what will happen? The third one, you can see the third picture, non-ductile column sway mechanism. In this case, what will happen? In this image, the third one stands for the soft story failure. So the hinges exactly formed in the soft story level, so the failure occurred exactly in the ground story. This story failure is generally referred as soft story failure. So the previous first two stands for ductile mechanism, whereas the last one stands for brittle mechanism. Brittle mechanism means immediate failure. Ductile mechanism means it's not immediate failure. So our building should behave like this. So during this deformation, your beam column joint is going to subject it to a huge distress. So in this case, our beam column joint should be able to resist large amount of deformation, large amount of shear force transformation. So our beam column joint is one of the weakest and very, very prime part of the building. So beam column joint in your building, in this picture you can see, the cornermost is generally referred as exterior beam column joint, whereas the innermost is generally referred as interior beam column joint, whereas the top corner is generally referred as corner beam column joint, as defined in this picture. Interior, exterior, and corner. So the stress transfer mechanism of the joint is very simple. All the loads and due to masonry wall will transfer to the beam. The forces in the beam will transfer to the column through the joint, and finally it will reach the foundation. So all the forces are traveling from every independent member through joint to the foundation. So joint is one of the very, very important member in transferring all the forces. So if the joint fails, we can expect a global failure. If the joint is not failing, then you can expect a localized failure. Localized failure means failure in any independent structural member, and globalized failure means the entire building collapse. So this is how the stress transfer mechanism is happening. So during deformation, during the ground vibration, our building is going to deform. So I told you the concrete is one of the very brittle material. So immediately the tensile stress level is going to be higher. So immediately you can expect cracks at different levels. So this cracks will allow the reinforcement to slip from its original position. This creates huge shear stress concentration in the beam column joint as defined in this picture. This leads to the collapse, shear collapse or shear failure in the joint. So these are the various shear failure of the joint, different joints, corner level, external level, interior level. So how to construct earthquake resistant structure? We have to design our building with respect to IS 1893. We have to detail the structure with respect to IS 13920. So what does it mean by design and detailing? Designing, we have to follow the procedure which is defined in 1893, which means the load cases with factor of safety. Whereas 13920, after designing the building with respect to 1893, you have to perfectly detail the building. That we will define, we will discuss in the later slides. So this is the planning stage. When you have a very long building, it should not have opening like this. This is generally referred as diaphragm discontinuity. So when you apply the force in one side, it is not going to transfer uniformly to the other side because of this opening. And come to the next case, stiffness irregularity. Stiffness irregularity means stiffness, you can see the first floor stiffness should be equal to the second floor, which is equal to the third floor, which is equal to the fourth floor. When your stiffness is not going to be same for first floor and second floor and third floor, that is generally referred as stiffness irregularity. So what will happen when stiffness irregularity occurs? So for example, our ground story height is 10 meter and the first story height is 6 meter, second story height is 6 meter. The ground story height is 10 meter. So it is going to be very slender as compared with the first story and second story. In this case, stiffness level of our ground story is very less as compared with the stiffness level of first and second story. So what will happen when the height of the first story is this much, height of the ground story is this much. So the slenderness creates the weaker stiffness part of the building. So this particular thing will lead the entire building fail due to the weak story or soft story failure. This will lead soft story failure. So it is perfectly defined in this picture.
It means the old multiplexes where we are going for a parking at the lower level at the ground story. It's a kind of soft story. It's going to be damaged very easily. Soft story.
Yes.
From parking.
So vertical strengthening is done to increase the strength of the building.
Yes.
Since the wall brickwork, soft building of the brickwork. Brickwork की depth बहुत कम होती है. It is 150 mm.
No, I'm not getting your point.
जो हम vertical sparring करते हैं, vertical put करते हैं, हम basically अब strength बनाने के लिए करते हैं.
Yes.
क्योंकि उस brickwork होता है. सर हम horizontal करते हैं 150 mm. तो maximum मैंने देखा है 150 mm horizontal ही करते हैं. Vertical बहुत कम करते हैं.
Where?
Everywhere in the high-rise building.
In RCC building.
High-rise building.
In RCC building.
Yes.
In RCC building, brick is going to.
Bring, sir, when we
In RCC building, brick is not
the question here, otherwise other people will not listen.
just a partition. Brick is just for partition. Okay. So in RCC building, we are not going to strengthen any brick wall. Just listen. In RCC building, we are not going to strengthen any brick wall. Brick is just a partition. It is not going to take any kind of load. Okay. So for example, I have a column. Internally, I have a brick wall. So when it deforms like this, immediately the deformation will transfer to the brick. Okay. So immediately the brick will fail. Brick is not able to resist any kind of force because it is a brittle member. So immediately the brick will fail. But the brick is perfectly confined between column and beams. So the stress due to this particular particular brick wall will transfer to this joint level at this connection. When it traveling to this direction, it will transfer to this joint. Okay. So if your brick wall is 300 mm thick, for example, the stress level is going to be very, very large. When you have very small thickness, immediately it will fail, it will fall down. That is the concept we are going to reduce the brick wall for partition size. Similarly, I told you, if you have a water tank on the building, the water tank is nothing but the heavy mass in the structure. So we should not have heavy mass on the structure or at any intermediate level. For example, take a scale, okay, and the scale is going to have a uniform weight. Scale is going to have uniform weight, stainless steel scale. The top of the scale, just keep one magnet of weight of around 200 gram. Now, the top of the scale having higher mass as compared with the bottom level. So when you vibrate, the vibration is not going to be the scale which has no magnet. So both the vibration is completely different. So that is why we should not have heavy mass at any level, which means mass irregularity. The mass of the first floor should be equal to mass of second floor. If not, heavy mass will create huge distress during an vibration. Similarly, vertical geometry, already I have defined in the previous slides. Similarly, in the plan irregularity, if you have any shape like T, L, or plus, or C, it should have a separation joint at different levels, every connections, so that the buildings will deform in an independent way. So our earthquake resistant design philosophy starts from a word called strong column, weak beam concept, which means column should be strong, beam should be weak. So that, see, our building, in our building is perfectly connected by column and beams. A building is perfectly connected by column and beams. Can we able to imagine the building without column? Anybody? No. But you can easily construct a beam. You can easily construct a horizontal beam in this direction, this direction, and this direction. You can easily construct. If you need a house, we need column. Okay. So column is one of the prime important member of the building. So if your column fails, the entire building will collapse. As I already have shown you one image that every floor is like pre-packed like a burger. That is because of column failure. Okay, so column should not fail. The reason why we are expecting beam should fail, we are not expecting the beam should fail. The beam should allow the entire building to deform exactly at the junction point. That's why we are generally referred as a big beam. So if you are expecting strong column, big beam, then your building should behave like the one which is defined in the third image, or like the fifth one. The plastic hinges should form like this at the foundation level, at the different beam column joint level. So if the plastic hinges are already formed in the defined level, then you can expect a ductile mechanism, or like the like the coconut tree deformation. Otherwise, it will fail like the banyan tree. That's a perfect example for strong column, big beam concept. We are not going for big column, strong beam concept. As defined in the first one, strong column, big beam. So when you have soft story failure, the displacement of building is very, very less. I told you our building should deform like the coconut tree. It should not deform like the banyan tree. So when you're expecting your building to deform like the coconut tree, the deformation should be very large. It should not deform in a very small way. So the first one is a perfect example for how it should not deform. The next one is a perfect example for how it should deform. When it deforms like this, you can expect a huge deformation as compared with the first one. This is generally referred as ductile mechanism. So for this case, this is the column and this is the beam. Okay, so when the building deforms, so we can expect this connection should deform. If the connection is not deforming, then we can't expect ductile mechanism. In this case, what we have to do, we are connecting, this is the column and this is the beam. Okay, so we are connecting the beam like this. What will happen if you are connecting the beam like this? When the entire building deforming, if the connection is not strong, the beam will fail. But we are expecting hinges to be formed in this particular connection. In this particular connection, if hinges are forming, this particular hinges will create huge stress transformation to the joint. So our beam connection should be very, very strong. In this case, what we have to do, if I have a connection like this, it is weak. Then what I have to do, my beam should perfectly connected internally into the column. Okay. So this is, for example, this is reinforcement. This is reinforcement. Okay. It is going into the column reinforcement like this. Now it is already into the column. Now these are vertical reinforcement from column. This is horizontal reinforcement from beam. Now it should be perfectly anchored. It should be perfectly anchored like this. If it is not perfectly anchoring, when the large deformation occurring in the building, this will pull up. This is generally referred as reinforcement slip from the connections. If it is perfectly connected like this, even if you apply load like this, it won't come. This is what defined in the IS code. So you can see in this picture, the vertical stands for column, the horizontal member is beam. The reinforcement, the top reinforcement is going down, the bottom reinforcement is going up. This is to anchor the beam with the column, so that the beam will not fail during an earthquake, because we are expecting the plastic hinge formation exactly at the beam column connections. If beam fails, there is no plastic hinge formation, so the entire building will fail again. So even after anchorage, we have to go for detailing. This is what IS 13920 defines. So designing is separate, detailing is separate. Even with the proper design, if you're not detailing the building will again fail. So what is detailing? Detailing means you have to give a detailed definition for the confinement and the reinforcement positions. That is why it is generally referred as detailing. So in this case, confinement plays very, very important. Basically, our concrete member or column member or beam member has two roles, or two concrete. One is core concrete, another one is concrete cover. Concrete cover plays role where durability speaks, and core concrete plays role when ductility plays. So for ductility, core concrete plays very crucial role. For durability, concrete cover plays crucial role. So in this case, earthquake resistant measure deals with ductility. So concrete cover has no role, just to cover the confinement. That's it. Our confined concrete, that is defined as core concrete, plays very, very important role. So in this case, we have to make the concrete so confined so that it can easily resist any kind of lateral deformation plus shear stress transformation. In this case, how to improve the performance of core concrete? We have to confine. So when you confine more, see, in this case, this is the column confinement. Internally, we have concrete like this. If it is not, if it is connected like this, we have a huge space between two stirrups. So what will happen during large deformation? This particular concrete between these two will immediately fail, immediately crush, so that the entire concrete, the concrete presence between the confinement is not going to resist any kind of force. Like when you have a confinement like the one, it's a very closer confinement. So I can easily confine the concrete which is present inside the confinement. That is generally referred as core concrete. So the core, we have to protect the core concrete from the large deformation so that it can resist the large deformation. So for this case, we need closer confinement as defined in the IS 13920. And our IS 13920 is not defining this critical confinement everywhere. It is defined only in the critical portions of the building. You have to follow certain codal procedures so that you can easily resist any kind of earthquake forces. If you're not able to follow, if you're not following, it is very difficult to resist any kind of forces. And very importantly, we are making hooks, that is stirrups. So that stirrups is not only in the beam column joint range, also in the foundation range, because we are expecting plastic hinge exactly at the foundation level also. The next one defines how the hook should be, that is stirrups. So it should not be 90-degree hook as defined in the third image. It should not have 90-degree hooks. We should have 135-degree hook with perfect inclination plus perfect projection internally, so that the anchorage will not fail, so that the hook will not release from its original position. It will remain as it is during a large deformation. It will perfect the concrete. It will perfectly confine the concrete. Otherwise, if you have 90-degree hooks, what will happen when the deformation occurs or when you apply large force? The 90-degree hooks will immediately open. When you have 135-degree hooks like this, it will not open. It will create a perfect link like this. When you have 90-degree hooks during the application of large axial force or large deformation, this will immediately opens, so we can't confine the concrete, so immediately the confined concrete will fail. And importantly, I told you, I have shown you an image. This file, the second one. In this case, I told you, even this is confined, even after confinement, it failed because they have done confinement in an improper way. They haven't done confinement in a proper way. So how it should be? This is a perfect example. When the member size is very, very large, we should not go for a single confinement. We should go for a multiple steps like defined in the second one and the last one. When the cross-sectional size is more than 300 mm, we have to go for multiple number of stirrups, or otherwise it is generally referred as 2-legged stirrups or 3-legged stirrups or 4-legged stirrups, or we have to confine in a multiple way. When you are confining in this way, you can easily protect any kind of structural member. So these are the various codal procedures defined as per our Indian standard. When you follow all these procedures, you can easily construct a new house to be an earthquake resistant one. But we can't construct, I can't construct a house. So what we can do, we are hiring a person from outside, a mason, and he is executing the building, a bartender. If you are asking him to go for 135-degree hook, he will tell you it will take too much time and it has no role and it is completely useless. So what will you do? You will accept the 90-degree hooks so we can execute. Similarly, a mason, he will tell you when you go for closer confinement, it is creating congestion, so I can't go for any perfect concreting work. So again, we are compromising over there. And when you go for any new construction, you can see they will raise the column up to the beam bottom. This is the beam, this is the column. So up to the beam bottom, they will raise the column. And then when you are inserting the reinforcement of a beam, you can't go for a perfect anchorage. Again, we are compromising here. So we can't provide perfect anchorage. So when you are doing all such mistakes, you can't resist any kind of earthquakes. So these are the various procedures recommended in IS standard. You have to follow these standard methods. These are traditional methods or conventional methods. So what are the methods already we have in advanced stage? We are going to look into a small overview about the alternate constructions or advanced techniques to resist an earthquakes. So earthquake is, I told you, is an inertial force. It is creating ground motion, and that's why our building is deforming like this. So we have to do lot of procedures so that we can easily resist any earthquake. We can resist any earthquakes. But the point is, when you are not able to follow like closer confinement, so instead of this much spacing between two stirrups, we are providing this much spacing. So we are losing the concrete between these two. So when you are not able to go for this, you have to choose alternate constructions. So alternate construction will allow you to go to some compromising, like you can increase the spacing, but without compromising in resistance of any forces. You can resist any earthquake forces even with higher spacing of stirrups by just introducing new advanced materials in the construction industries. So let us see into the alternate construction techniques. One of the very easily available material, generally referred as fiber, in the form of metallic or in the form of synthetic. So you can see in this this concrete is generally referred as fiber reinforced concrete. What does it mean? We have a normal concrete composed of aggregate, that is coarse aggregate, fine aggregate, cement, and water. This is the normal composition of your conventional concrete. Whereas in this case, cement plus fine and coarse aggregate plus water plus fiber. Then that is generally referred as fiber reinforced concrete. So this is example for synthetic fiber. This is example for steel fibers. So when you are adding this kind of fibers, what is happening? It is improving the stress strain behavior. See, the first one is for plain concrete, where we don't have any fibers. The strain is very less as compared with the steel fiber reinforced concrete. When you can resist large strain, then your concrete has very good strain capacity. When you are concrete having very good strain capacity, that concrete can go large deformation. That is the meaning for this. Okay, so this adding of these kind of fibers will improve the tensile behavior of the concrete so that you can easily resist any crack formation and you can go for large deformation as compared with the plain concrete. You can see the failure pattern of plain concrete and steel fiber reinforced concrete. In the plain concrete, part of the concrete surface is completely spar. When you look into the second one, because of the presence of steel fiber, it perfectly connects even the failured one, even the cracked one with the existing one. There is no any concrete spalling. This is the advantage of fiber reinforced concrete. So when it deforms in a flexural way, if you have fibers in the beam, it will perfectly bridge the cracks. So when you have just See, this is the beam. When I'm applying load, there is a crack formation is like this. In the conventional concrete, if the crack opens like this, what will happen? This crack will open and finally the beam will become two half. When you have fibers, it will bridge the cracks. Okay, so if I have fiber between these two cracks, what will happen? It will not allow the crack to form or crack to grow easily. It will bridge or it will stitch the cracks perfectly. So until the entire fiber fails, the crack formation or crack growth will remain very slow. And once the entire fiber fails, then the crack formation will be very, very high. So the crack formation is very, very important in the failure stage. Once the crack formed, so in the conventional concrete, there is no any method to bridge the cracks, so immediately failure will occur. Whereas in fiber reinforced concrete, the fiber present between the cracks will perfectly bridge the cracks, will allow the crack to grow in a very gradual rate as compared with the plain cement concrete. So these are the advantage of fiber reinforced concrete that will resist cracks formation, that will improve the damage tolerance capacity, that will add tensile behavior to the concrete, and that will allow the entire structure to deform to the larger extent, to the larger deformation without going for any critical confinement in the joint region. So this is the one of the example. So the first beam column joint have detailed as per 456 gravity loading. The next one 13920 is detailed as per 13920 earthquake resistant measures. And now these joints are constructed with normal concrete and steel fiber reinforced concrete and is subjected to an earthquake force. Now you can see the first one, first failure pattern. Okay, first failure pattern stands for 456. Second failure pattern stands for 13920 detailing with plain cement concrete. Come to the case of third one, that is steel fiber reinforced concrete with 456 detailing. There is no earthquake resistant measures detailing. Okay, even with there is no any spalling of concrete, but it has very good load resistance capacity and crack resistance capacity. There is no concrete spalling in the joint region. This is the advantage of steel fiber reinforced concrete. Similarly, if you are expecting that if you are going to construct a house in zone number 5 and the building height is very, very high, so what will happen when you increase the building height? The building vibration is also going to be very, very high. So in this case, your conventional concrete method is not going to work. Even the fiber reinforced concrete is not also going to work. In this case, what we can do, we can go for advanced level. For advanced level, that is generally referred as fiber reinforced cementitious composite. I told you in conventional concrete, we are using cement, coarse aggregate, fine aggregate, and water. In fiber reinforced concrete, we are adding fiber with the conventional concrete. Whereas in this case, there is no coarse aggregate, there is no fine aggregate. See, in this case, we are adding cement, fine aggregate plus mineral admixtures. Mineral admixtures nothing but silica fume, fly ash, or GGPS, anything. Such a waste material and very, 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 very fine material that will fill the pores present between the sand. Water, admixtures, and fibers, that is defined as high performance fiber reinforced cementitious composites. It is not concrete. It is cementitious composites. You can see this will work far better than steel fiber reinforced concrete or any fiber reinforced concrete. So that's why these kind of composites are recommended for the building requires large deformation. When you're using this, the large deformation, and this is not recommended for the entire building. It will cost you a lot. That's why it is recommending only in the joint region. So when you're using different kind of fibers in the joint, you can make the composite like this. So these are various failure patterns. You can see the previous conventional one, we can see concrete spalling. In fiber reinforced concrete, we can execute or we can expect a huge number of cracks. Whereas in this kind of composites, you can see the joint is perfectly safe from the collapse. So these are internal measures. When you come to external confinement means what? I told you for the existing building, how to save the building by using some external measures for masonry structures. For RCC building, this is the only way we can improve the performance of the building, or we can save the building from any lateral deformations. This is generally referred as external confinement using fiber reinforced polymer sheets. This is how they have to perfectly confine the external part of the building at different levels, exactly in the joint level. When you confine exactly in the external region, this will create or this will induce triaxial force. Internally, we can expect two force and externally one force, that is triaxial force. This triaxial force will perfectly confine the structure, especially the joint region, and it can save the structure from collapse. Another one is, the last one is base isolation. So what is base isolation? So when you have a base isolation, like there is a difference between traveling in normal bus and Volvo bus. So what is the difference between traveling in the normal bus and Volvo bus? Anybody?
Comfort.
How do you feel that? How do you feel the change in the comfort? Space, only space.
Seats are comfortable.
Seats are comfortable. Next.
What do you feel in ordinary bus? What happens?
See, when you're traveling in a normal bus, and suppose the normal bus is crossing one speed break, okay, that's why we have shock absorber at different levels. Okay, so anyhow, the shock absorber will dissipate the force. These forces will transfer to the platform of the bus. So our seat is perfectly fixed with the platform. So you can feel the vibrations. Okay, in the normal bus. In Volvo, have you ever traveled in Volvo? Yes. So if the Volvo bus crosses the speed breaker, how do you feel? Why? Huh? Why? What's the difference? What kind of technology? See, in the normal bus, the shock absorber is connected with the wheel. Whereas in Volvo, always it is not going to be in suspended level. If the engine is off, the bus will coming down. The bus will come down automatically. When you switch on the engine, and if you switch on the engine after giving the acceleration, this bus will go up. Then intermediately they have air suspension. Okay, when the bus moves, if it crosses the any speed break, the bottom portion is different, top portion is different. The top portion is perfectly connected with your seat. So when you feel the vibration alone, you can feel the vibration, but the entire body will, like in the Volvo bus, when you sit like this, the bus will move like this. You will also move along with the bus. That's why you are not feeling the vibration. Whereas in the normal bus, it is not like this. This is because of the suspension between the bottom platform and the top platform. This is what we are trying to create in the base isolation. In this case, you can see the first one, fixed base building. So the top building is perfectly fixed with foundation, whereas the second one is isolated. So the entire building is resting on the isolation. So when you have fixed base, the building will behave like defined in the third one. When you have isolated base, the building will behave like as we defined in the fourth one. That is the difference between in the deformation stage when you introduce base isolation technique. This isolation can be using different materials. So this is how, when you use base isolation technique in RCC building, this is how the building will behave. And this is how the building will behave when you have fixed base that is defined in the second one. So the bearings may be at different level. We can use different type of materials in bearing. The first one is elastomeric bearing. The next one is roller pin bearing. The third one is friction based bearing. So this is how the bearing will allow the building to deform. You can see this is the deformed bearing. So this is the internal part of the elastomeric bearing. Internally, we have a lead core or any solid core, because the entire building is going to rest on the bearing. So the bearing should have ability to resist the compressive force. If you have rubber band, this is not going to resist. That's why in this internal, you can see the internal structure of the bearing. Internally, we have a solid lead core and supported by rubbers and steel plates. This will take the axial load as well as lateral deformations. This is another bearing. This is also another bearing. Next one is active damping system. So when you're constructing a building of height 10 story, it is okay. When you're constructing building of 20 story, 30 story, 40 story, 100 story. So we can't design the building by considering the earthquake forces alone. When you're constructing a building for 10 story, then there is no need to construct the wind force when you're considering earthquake force. Earthquake force is larger than wind force up to a certain height. Okay, when you're going for a 100-story building, it is very difficult to consider earthquake forces alone. So the deformation at different level is going to 100-story building means it is going to have 100 mode shapes. It is going to have 100 different mode shapes. So the mode shape is nothing but the deformed shape of the building. So it is going to have sinusoidal deformation at different levels. So it is very difficult to make the building to a earthquake resistant one. In such cases, you may ask me, why can't we go for damping system? We can go, but the cases, if your building is very slender, the damping is also not going to support you a lot. That's why we have to go for damping, active damping system. It's not going to be base isolation. It is going to be active damping system. How the active damping system will help you to resist the lateral deformation? Let's see in a video. You can see the first building has no active damping system, whereas the second building have a damping system. So when the building is subjected to vibration, how the active damping system is going to help you to resist the lateral deformation? You can see or you can experience from this video. Now they are giving lateral forces using a small stake table. This is how active damping systems are helping you to resist the lateral force. So this can be easily implemented. You can easily fix this damping system everywhere in the building because it is external part. It is not going to be the internal part. You have to connect the link between column and beam as defined in this picture. Okay, so this particular damper has many things like viscous damper, friction damper. So based on the requirement of the building, we have to choose the damper and you have to choose the location of connections. It can be connected in L shape, X shape, or any shapes like defined in this picture. So this is a perfect example how they have connected the damping system in the existing building. So this is how the damping system will help you to reduce the deformation or to resist any deformation during an earthquake. Thank you.